Hello and welcome back to Wizako's GMAT podcast. My name is Bhaskar. In this episode, we are going to be looking at one thing that we left unfinished in the last episode. In the last episode, we dealt with concepts about types of numbers. Essentially, the number systems is what we focused in the last episode. We ended that episode with 3 questions. 1 problem solving question and 2 data sufficiency questions to get us a feel about what kind of questions will that concept translate to in the GMAT. This episode, we're going to be looking at solutions to all of those 3 questions. Let's get started with the first one. The first question would have been a 600 level GMAT question. It's a medium difficulty question. It's not very difficult. I'll read the question and then let's quickly run through the answer options and do the solution for it. Which of the following numbers is irrational was the question. We had 5 answer options. Let's start with the first one. Answer option A was square root of 20 upon 45. Now let's just look at the fraction alone. Let's keep the square root aside for a moment. The fraction is 20 upon 45. Both 20 and 45 are divisible by 5. Let's divide the numerator and denominator by 5. That will leave us with a 4 upon 9. So square root of 20 upon 45 will reduce to square root of 4 upon 9. This can be written as a square root of 4 divided by square root of 9. Square root of 4 is a 2. Square root of 9 is a 3. So the net answer is 2 upon 3 or a 2 by 3. 2 by 3 is of the form p by q, where p and q are integers such that q is not equal to 0. It's a fraction, so therefore it is a rational number. Our question is to find out numbers which are irrational. This is a rational number, so it is not irrational. Answer option A is not our answer. Let's move on to answer option B. The number given there was 7 root 3 divided by square root of 27. I'm going to take the denominator square root of 27 and rewrite the 27 as a 9 times 3. So what we'll end up getting is 7 root 3 divided by root 27 will become 7 root 3 divided by square root of 9 times 3. We can take the 9 out of the square root. That will become a 3. So 7 root 3 divided by root 27 will end up becoming 7 root 3 divided by 3 root 3. We have a root 3 as a term both in the numerator and the denominator. It will cancel with each other to leave us with an answer which is 7 by 3. It's a fraction. Therefore, this is also a rational number. The answer option B is not the correct answer. Let's move on to answer option C. This is 1 upon root 64. It's a very simple one. 64 is a perfect square. So root 64 is an 8. So 1 upon root 64 is equal to 1 upon 8, which is a fraction. Therefore, it's a rational number. Answer option C is also not irrational. So that's not the answer. Let's move on to answer option D. Answer option D is 7 upon 3.1. We'll multiply both the numerator and the denominator by a 10. So we'll end up getting 70 upon 31. 70 upon 31 is a fraction where both p and q are integers. So it's a rational number. So answer option D is also not the correct answer. It's not an irrational number. So that leaves us with only one option. E has to be the irrational number. Let's quickly see how it becomes an irrational number. The rationale behind it becoming an irrational number. The number is square root of 36 upon 63. Let's just focus on the fraction right now. 36 upon 63. Both 36 and 63 are divisible by 9. So let's divide both the numerator and denominator by 9. We'll end up getting a 4 upon 7. So square root of 36 by 63 is equal to square root of 4 divided by 7. Square root of 4 divided by 7 can be written as square root of 4 divided by square root of 7. Square root of 4 is a 2. So net answer is 2 divided by root 7. 7 is not a perfect square, so you're going to be left with only a root 7. 2 divided by root 7. Root 7 is irrational, which means 2 divided by root 7 is also going to be an irrational number. Choice E is the correct answer. The 600 level question, you have to actually simplify it to get to the answer. It's not possible to just look at the numbers and say which is going to be rational or which is going to be irrational. They're not going to make it that easy, but it is not a difficult question. Let's move on to the second question. That's a data sufficiency question. If you have not done data sufficiency questions in the past, my suggestion is please pause this podcast right now. Go to the YouTube channel of Wizako, which is youtube.com/Wizako, Wizako. You will find a playlist called Data Sufficiency. Play the first video in the playlist. It's a 30-minute video. It'll give you a good starting introductory lesson on how to solve data sufficiency questions and all the different answer options. Go through it and then come back to the podcast. Those of you who are already familiar with data sufficiency, let's get started with question number 2. Question number 2 is a 650 level question. The question basically was this. Is the positive number x an integer? The question stem tells us that x is a positive number. What we need to answer is whether that number is an integer. Let's start with the first step. What is the question? The question is an is question. Is questions, what kind of answers will an is question get? An is question is going to be getting an answer which is an yes or a no. For example, we'll ask, is today a Monday? If today happened to be a Monday, you're going to be answering it with an yes. If today happened to be a Wednesday, you'll say the answer is a no. So is questions will have to get yes or no as an answer. If you get a conclusive yes, the data is sufficient. If you get a conclusive no, the data is sufficient. But if you say, hey, sometimes it's an yes, sometimes it's a no, which is when the data is not sufficient. Right? We got clarity on what kind of an answer we should get, when is the data sufficient. Let's get around to evaluating the two statements. Let's start with statement 1. Statement 1 tells us that 5x is an integer. The approach I'm going to take to solve this question is basically this. I'm going to look for a counter example. What do we mean by a counter example? A counter example is one where we'll pick this information 5x as an integer and that is going to hold good. For one of those examples, when 5x is an integer, we'll get an answer that x is an integer. If you are able to find one more example where 5x is still an integer, but x is not an integer, then we can go ahead and say, hey, you said 5x is an integer. I've got two values. In both the cases, 5x was an integer. One instance, x happened to be an integer, and in the other one, x was not an integer. So despite knowing 5x is an integer, I'm not able to answer your question whether x is an integer. Let's find an example for 5x being an integer and x also being an integer. Take 5x to be a 5. Is 5x an integer? Yes. If 5x is a 5, what is x? X is equal to 1. Is that an integer? Yes. So I found an example where 5x is an integer and x is also an integer. Good. Let's look at a counter example, an opposite example. 5x should be an integer, but x should not be an integer. Let's go with 5x equals 4. Is 5x an integer? Yes, 5x is an integer. Is x an integer in this case? X is a 4 upon 5, which means it's not an integer. So we have found an example where 5x is an integer, but x is not. We could find an example where x was also an integer. We could find a counter where x is not an integer, which means knowing that 5x is an integer is of absolutely zero value in determining whether x is an integer. So statement 1 has been not of help to us. Statement 1 is not sufficient. If you had gone through the video about the process, the moment you realize that statement 1 is not sufficient, you can eliminate answer options A and D. That leaves us with three options, B, C or E. To check which one this is, we're evaluating statement 2 alone to start with. Statement 2 tells us x upon 5 is an integer. So let's write it in terms of an equation. So x upon 5 equals I. Let's say I is an integer. Capital I is an integer. So if x upon 5 equals I, cross multiplying the 5, we'll get x is equal to 5 times I. 5 times I is 5 times an integer. 5 times an integer is definitely an integer. You multiply 5 with any integer, the answer has to be an integer. Which means what have we got? We got x is an integer. So if x upon 5 is an integer, x definitely will have to be an integer. It cannot be anything other than that. Statement 2 has given us a definite yes, a conclusive yes, without an iota of doubt. So statement 2 alone is sufficient. Statement 1 was not sufficient. Statement 2 is sufficient, which means answer option B is the correct answer to this question. Let's move on to the third question. This is a tad bit more difficult. This question I'll classify it as a 700 level question. I'll read the question, the statements, and then let's set about solving it. If A, B, and C are non-zero numbers, how many of these three numbers are positive? Let's get started with what all information it's saying. They've given us three numbers A, B, and C. They've said that those are non-zero numbers, which means those numbers could be positive, those numbers could be negative. When I say numbers could be positive, numbers could be negative, keep this thing in mind. The numbers need not necessarily be integers. 0.3 is a positive number, minus 8.4 is a negative number. They have not said these numbers are integers, so they need not be integers, but the only thing that we know from the question stem is these are non-zero numbers. What is the question asking us to find out? It's asking us to find out how many of these three numbers are positive. 4 possibilities exist. None positive, 1 positive, 2 positives, all 3 positives. But you cannot say either 2 or 3 could be positive. That is not allowed. You should come up with one single answer. You should be able to say, I know for a fact so many of these numbers are positive. Let's set about finding it out using the statements. Let's start with statement 1 as always. The sum of these three numbers, A plus B plus C, is greater than 0. So sum of the three numbers is positive. Let's see if we can eliminate some possibilities within that. Is it possible that the sum will be positive? Will all three numbers being negative, A is negative, B is negative, C is negative, can the sum be positive? That is not possible. So all three numbers being negative, which is none of the numbers being positive, is not a possibility. So that is ruled out. So of the four, we know one certainly is not there. Can we have one positive number and two negative numbers and the sum can it be positive? Certainly yes. If the magnitude of the positive number is greater than the sum of the magnitudes of the negative number, this is going to happen. Let's take an example to see this. Let's say A is a positive number, which is equal to 10. B is equal to minus 2. C is equal to minus 3. The sum of these three numbers is going to be positive. So one positive, two negative, the sum can be positive. Can two of these numbers be positive and one be negative and the sum be positive? Certainly yes. Take A to be equal to a 10, B to be equal to a 5. These two numbers are positive. C is a minus 1. The sum is positive. Can all three of them be positive and the sum be positive? Absolutely, no doubt at all. So from statement 1, we don't have a single answer. We have just ruled out one possibility. We are saying that still three possibilities exist. One of these numbers is positive, two of these numbers are positive, or all three are positive. We are giving three possible answers, which means statement 1 is not sufficient. We have not got a unique answer. If we have said that statement 1 is not sufficient, we can eliminate answer options A and D. Statement 2 states that the number of negative numbers is more than the number of positive numbers. We have three numbers. They're saying you've got more negative numbers than positive numbers. When you're evaluating statement 2, evaluate statement 2 alone. Forget ever having read statement 1. So all that we know right now is that we have more negative numbers than positive numbers. Let's see what all possible combinations can exist with this. Can all of the three numbers be negative? Yes. 3 negative, 0 positive will have more negative numbers than positive numbers. So that's one possibility. Can we have two negative numbers and one positive number? Yes, 2 negative, 1 positive. There are more negative numbers than positive numbers. This is also a possibility. Can we have one negative number and two positive numbers? No, the number of negative numbers is not greater than the number of positive numbers. Certainly we cannot have 0 negative and 3 positive and satisfy the condition given in statement 2. So if statement 2 were true, then how many possibilities we have? We have 3 negative and 0 positive, or 2 negative and 1 positive. So how many of these numbers are positive? We're still left with two answer options. None of them need to be positive, or one number can be positive is what we end up with. So statement 2 is also not sufficient because it gives us two possibilities. With that, we can eliminate answer option B. So that leaves us with combining the two statements. Let's just quickly check out what all possibilities existed with statement 1. Statement 1 gave us three possibilities. One of these numbers is positive, two of these numbers could be positive, or all three could be positive. So we had three possibilities with statement 1. Statement 2, what all possibilities did it leave us with? It left us with the possibility that none of these numbers need to be positive, or one number is positive. If the information given in both the statements need to be true, check out if there is anything that's common between the two statements. 1 positive, 2 negative is a possibility for statement 1. 1 positive, 2 negative is also a possibility for statement 2. Let's just pick that possibility and see whether both the statements hold good for a moment. And then if that is true, then we have a conclusive answer. If you have two negative numbers and one positive number, can the sum be greater than 0? Yes. The two negative numbers, let's say, are A equals minus 2, B equals minus 3. The sum right now is minus 5. I pick a positive number whose magnitude is greater than 5. The net result is going to be positive. Let's take an example. Minus 2, minus 3 and 10. So the positive number is 1 in number. The positive number has such a great magnitude that the sum of all these three numbers ends up being a positive number. So statement 1 holds good with one positive number. Will statement 2 hold good? Yes, I have one positive number and two negative numbers. So there are more negative numbers than the number of positive numbers. So if two statements are taken together, if both these information are true, then the only value that satisfies it is when we have one positive number. Combining the two statements, we have a conclusive, definite answer that one of these three numbers is positive. Statements together are sufficient. Statements together are sufficient. Answer option C is the correct answer. Beautiful question, the third one. There's nothing that's not known to us in it. But these questions are the ones which are the juicier ones that you tend to get in the data sufficiency part of the GMAT. Next episode, we're going to be starting with concepts on prime numbers and composite numbers. So to end this, I'm going to ask you a very simple question. Look at any tens, for example, numbers from 10 to 19, numbers from 20 to 29, numbers from 30 to 39. In any of these tens, what is the maximum number of prime numbers can you see? Until next time, Stay healthy, stay safe, and stay motivated.